Good morning, boys and girls. Welcome to day 2 of LHopital's rule. In this lesson, we're going to find different indeterminate forms and learn how to use LHopital with those. So on yesterday, we looked at the LHopital indeterminate form of 0 over 0 and infinity over infinity. Today, we're going to discover some new indeterminate forms. So infinity over infinity, which we talked about yesterday. And a lot of students are surprised to hear that infinity times 0 is also indeterminate. Infinity minus infinity, 1 raised to the infinity, 0 to the 0, and infinity to 0. All of those are indeterminate forms that you need to be able to recognize. I know some of them are blowing your mind because you thought anything 1 raised to any power is still 1. And anything times 0 is 0. However, in calculus, we find that that is not the case. And so these are all indeterminate forms. I would suggest that you make a list of indeterminate forms and put them in your bedroom or somewhere that you can refer back to them easily. So I would suggest you make a poster with all the indeterminate forms on them. So when you get to a problem, you can say, hey, wait a minute, is that indeterminate form? And then you can check. So we know from yesterday that infinity over infinity is we can handle that just like we do 0 over 0. But in the other ones, before we can use LHopital on it, we have to put it in the form of infinity over infinity or 0 over 0. Again, I would make a poster of this and I would memorize it. So let's look at the first an example quickly. We have the limit as x approaches infinity of x times the sine of 1 over x. Well, as we go towards infinity, we're going to get infinity, and then the sine of 1 over x. 1 over x, as x goes towards infinity, behaves like 0. So we get infinity times 0, which we know is indeterminate. So I have to rewrite this so that it is in 0 over 0 or infinity over infinity. So we should know that x can be written as 1 over x. The two are equivalent. So what we did here is we said that x, sorry, wrong pen, that x is equal to 1 over x. And if you're struggling with that, just think about it. We're going to divide. So when we would evaluate this, we would divide by the reciprocal, which would be 1 over x, then we get the same thing. So this is something that you need to recognize and be able to do quickly. And once we do that, now we have sine of 0 over 0, which is 0 over 0, and that's indeterminate form. Now we know from before that this is equal to 1, but let's just prove it using LHopital. So we're going to take the derivative of the numerator and divide it by the derivative of the denominator. When I took the derivative of sine over 1 over x, I had to use chain rule. The negative 1 over x squares will cancel each other out. And now I have the limit as x approaches infinity of cosine of 1 over x. The limit of 1 over x as x goes towards to infinity is 0. So I have the cosine of 0, which is 1. Okay, boys and girls, here's another example. We're looking at the limit as x approaches 1 of 1 over the natural log of x minus 1 over x minus 1. We do a quick direct substitution. The natural log of 1 is 0, so we have 1 divided by 0, and we say that that is infinity. It's going towards infinity. And the same as if we do 1 minus 1 in the denominator in the second term, it's also going to give us infinity. So this is our second indeterminate form, which is infinity minus infinity. Now, a lot of you are going to want to say that that's 0. It is not, because one could be growing faster than the other. 1 could be, they could be growing at a rate so that there is a number. So we can't say infinity minus infinity is 0. So what do? We have to put it in infinity over infinity form or 0 over 0 form so that we can use L'Hopital. So we're going to find the common denominator and subtract. So now when we do the limit as x approaches 1, we get 0 over 0. Therefore, L'Hopital applies. So once we use L'Hopital, we're going to take the derivative of the numerator and the derivative of the denominator. That will give us negative 1 over x, and we have to use product rule, or yeah, we're going to have to use product rule regardless on the bottom, and that's what we get. So now we have to do a little bit of algebra and get rid of all the x's in the denominator, so we're going to multiply both the numerator and the denominator by x. And we get that. Okay? All right, so that all I did there was clear the fractions, but notice when I do a direct substitution, I get 0 over 0 again. So I'm going to have to use L'Hopital once again. So now that's me taking the derivative of the numerator and the derivative of the denominator. And so now when I do a direct substitution, I'm going to get 1 over 2. And that's my answer. Okay, in the next few problems, we're going to have to recall that some logs that we've gone over just recently. So remember the natural log of x to the a drops. And if the natural log of y is equal to x, then e to the x is equal to y. Those are some things that we're just going to have to remember from Math 3. Okay, so if we were to look at the limit as x approaches infinity of x to the 1 over x, if we do a direct substitution, we get infinity to the 0, which is one of our indeterminate forms. So how do I use this so that I can put it in the form of 0 over 0 or x over x? So in order to do that, we're going to use log differentiation. So I'm going to set y equal to the limit as x approaches 1 over x, as x approaches infinity. Then I'm going to use some the property on it. I'm going to take the natural log of both sides. And once I take the natural log of both sides, I'm going to use the property on it. And once I've done that, now the natural log of x over x, as x goes towards infinity, that's infinity over infinity. Now we should know by now that that is 0 because x grows faster than the natural log of x. So that limit as x approaches infinity of the natural log of x over x is 0 because x grows faster. So that gives us the natural log of y equals 0. But I don't want to know what the natural log of y is. I want to know what is that limit. And y is equal to the limit. So I have to figure out what y is. So in order to figure out what y is, I have to exponentiate both sides. And I get y is equal to 1. So the limit as x approaches infinity of x to the 1 over x is equal to 1. Okay, boys and girls, here's another problem. And if we were to do a direct substitution, we see we get infinity minus infinity, which is an indeterminate form. So we're going to get infinity minus infinity. So we need to change it either to the form 0 over 0 or infinity over infinity. So how do I do that? I'm going to find the least common denominator. So I have the limit as x approaches 1. I'm going to find the least common denominator, which is x natural log of x minus x plus 1 over x minus 1 natural log of x. Alrighty, when I do a u substitution here, the natural log of 1 is 0, so that's 0. That's 0. So I get 0 minus 1 plus 1, which is 0. And then if I do, oh, I was about to write that the wrong way. Okay, I don't want to teach you bad habits. So this is the limit. I have to say the limit as x approaches 1 of x, natural log of x minus x plus 1 is 0. Then I have to do the limit as x approaches 1 of x minus 1. The natural log of x is also 0. Therefore, LHopital. Okay, so now that I know how to use LHopital, I'm going to take the derivative of the numerator. So I'm going to have the limit as x approaches 1. Take the derivative of the numerator, so I have to use product rule. I keep x the same, and then I get 1 over x, plus I take the derivative of x, which is 1, natural log of x, minus 1 over x, natural log of x. I already know what that is. That is, from here, I know that that's 1 plus the natural log of x. And then negative 1 times the natural log of x would just be negative 1 over x. Let's get rid of let's find the least common denominator. So I have the limit. So right now this is not calculus. I just have to do some algebra on this. I have 1 plus negative 1. That's just 0. So I have the natural log of x. And if I multiply everything by x, I get x plus x, natural log of x, minus 1, divided by x, which is the same as multiplying by x in the numerator. That's just algebra. So if I lost you on there, just do the algebra there. And now I'm going to do the derivative. I'm going to do the limit as x approaches 1. So taking that limit, I get the limit as x approaches 1. I'm not going to rewrite that out. I'm running out of room. I hope I have enough room. If I take that limit, I get the natural log of 1 is 0. And if I do it here, I get 0 again. Now I got to use LHopital again. All right, I can't write 0 over 0, and I'm running out of space here, so I'm just going to erase it. And you guys just know that we have to use LHopital again. Oh, kind of messed up my little triangle there. We're going to use LHopital again. So I have to use product rule again. I already know that x natural log of x is this, so I'm not going to do it again. I know that that is 1 plus the natural log of x over 1 plus 1 plus the natural log of x. And so now when I take that limit as x approaches 1, I get 1 over 2, a half. That was similar to the problem that we did before. Okay, this is the problem where we're going to have to use logarithmic differentiation. So if we take the limit as x approaches 0, we get 1 to the infinity, which is indeterminate. So this is 1 to the infinity. I don't know if College Board minds if you write that, but it's indeterminate. So now we're going to have to put it in the form of x over 0 over 0, infinity over infinity. So we're going to start by doing logarithmic differentiation. We're going to set this equal to y equals the limit as x approaches 0 of 1 minus 2x to the 1 over x. And then we're going to take the natural log of both sides. And that'll give me the limit as x approaches 0 of 1 over x the natural log of 1 minus 2x. Doing a direct substitution, I get 0 over 0, so therefore LHopital applies. And so now I'm going to take that derivative. And yeah, I am being a little lazy and not writing that because I don't have enough room, but you need to write that down. So this is the limit as x approaches 0. I'm going to take the derivative of the natural log of 1 minus 2x. I have to use chain rule. So that is negative 2 over 1 minus 2x. And then the derivative of x is just 1. So we do a direct substitution. We get the natural log of y is equal to, doing a direct substitution, I get 0, I get negative 2. Is that my final answer? No, because I'm not looking for y. Y was equal to the limit. So I'm looking for that limit, so then I have to say that e to the negative 2 is equal to y. So my answer is e to the negative 2. This is another fun problem. We have the limit as x approaches infinity of x squared, the square root of x squared plus x minus x. So as this goes towards infinity, we can see that this is going to give us infinity minus infinity, which is indeterminate. So what should we do here? Well, let's multiply by the conjugate. So we have the limit as x approaches infinity of the square root of x squared plus x minus x times, we're going to multiply by the conjugate, which would be the square root of so we have the square root of x squared plus x minus x, and the conjugate of that would be the square root of x squared plus x over the square root of x squared plus x plus x. Okay, we're multiplying by 1, so we're not breaking any laws there. So multiplying the radicals together would give me x squared plus x minus x squared over the square root of x squared plus x plus x. Now as I go towards infinity, well, these two will zero out, and I'm going to get x in the numerator. I get x in the numerator, and the square root of x squared plus x plus x. Now, if I do a direct substitution, yes, I get infinity over infinity. But the problem with this is that this radical will not go away. And I will continue to get that in some form or another. So instead of doing that, I'm just going to use some magic. Not magic, but some math common sense. Okay? We know, I'm going to come over here and do this. We know the limit as x approaches infinity of x squared plus x. Eventually, as we go towards infinity, the x become negligible. And so that looks like the absolute value of x, which we talked about before. Because the square root of x squared is just x, and because we're squaring it, it will always be positive. So that's going to look like the absolute value of x. So what I'm going to do is then, since I'm going towards infinity, this will always be positive, and this one is always positive. So I end up, it looks like x over x plus x, or x over 2x. So the limit as x goes towards infinity is 1/2. Okay? Yeah, I know. You're excited about that problem, aren't you? All right, last one. It's another one where we're going to have to use logarithmic differentiation. If I do a direct substitution of 0, I get 1, and cotan of 0 That's cosine over sine. So sine is in the denominator and it's 0, so it's going towards infinity. So that's another one that gives me 1 to infinity. So what do? I am going to have, so this is indeterminate form 1 to infinity. So I'm going to say y is equal to the limit as x approaches 0 from the right of 4x plus 1 raised to the cosine x. I'm going to take the natural log of both sides. This is a lot of writing. And then, of course, when you're doing this on your own, if it's just multiple choice, you don't have to do all the writing, but if it's free response, you got to do all this writing. Okay, so I took the natural log and I dropped cosine x. As it approaches 0, I get, oh, that's cotan x. I was like, well, that's not going to work. That's cotan x. That's cotan x, sorry. As we approach 0, I get the natural log of 1, which is 0, and then cotan x is infinity. So I get infinity times 0, which is indeterminate. And I'm trying to put it in the form either 0 over 0 or infinity over infinity. So that is going to give me the natural log of y is equal to the limit as x approaches 0. So to put it in the form that I need, I can say this is equal to the natural log of 4x plus 1 over tangent. So now that gives me 0 over 0, and of course that's how I'm going to write it. I'm going to write out that first one and say the limit as x approaches 0 of natural log of 4x plus 1 is 0, and then the limit as x approaches 0 tan x is 0, therefore L'Hopital applies. That's what you're writing. My wrist is hurting, so I'm not writing that because of the way I have to write on this laptop. Alrighty, so then what do? I'm going to use L'Hopital. So I have the natural log of y is equal to the limit as x approaches 0. I'm going to take the derivative of this, which is going to be 1 over 4x plus 1 times 4. And the derivative of tan x is secant squared x. Okay, now as I approach 0, I get 4 over 1. Is that my answer? No, that's the natural log of y is equal to 4 over 1. So y is equal to e to the 4th. And this is my answer. Oh, that's a lot of work. Okay. All right, boys and girls, that's all I have for this lesson, which is quite a bit. It's 23 minutes, sorry. And we'll practice this some more tomorrow. And I'll see you later. Practice it. That's all the way we